All right, recall. So here's an interpretation of what we were doing last time. Let's say you flip a coin 100 times and it comes up heads 40 times. Is it fair or isn't it? Let's find out, okay? So you flip a coin 100 times and it comes up heads 40 times. Is it fair? Do you have reason to believe that the coin is actually a fair coin? Of course it can come up 40 times. It's not going to come up exactly 50 times every time you flip a fair coin 100 times, right? Is it fair or isn't it? So let's work this out. How would we determine whether or not the coin is fair? Well, yeah, Taylor?
Can I measure how much the average of that is far away from a fair coin's average?
Yes. Yes. What would we do to figure out, what does it mean for the coin to be fair? Amelia?
If the difference of means between like 40 and 50 is significant?
Yes. If the difference of means, yep, that's going to be, it would be a difference of means problem if we had two coins that we were comparing.
Oh, because they have to both be random.
Yeah, the other coin isn't a random thing. It's fair means it's a 50% coin, right? So what does it mean to be fair? Fair is that, what is a coin? A coin is a Bernouilli trial, Bernouilli random variable, with presumably every time you flip it, you're not a magician who can flip it heads every time, right? Percy Diaconus can flip it heads every single time. If you're just actually flipping it, then there's probably a 50-50 chance, or theta and 1 minus theta chance of getting heads, with probability that each of these is 1 being equal to some parameter theta. So, being fair is that theta is a half, right? So fair, i.e., is theta equal to 1/2? Well, theta hat, our estimator for theta is from either the moment method or the maximum likelihood method.
0.4.
X bar, the average, exactly. X bar is 0.4. So you would say, well, no, it's not fair because X bar is 0.4 and we're expecting a half. That's a point estimator. We want to do better. We want an interval estimator. Right? That's the whole. I'm just reviewing what we're doing last time, but through the lens of an actual experiment. So this is a point estimator. Estimation. And with a point estimation, you can't tell. Am I close enough to a half? Does 0.4 look like 0.5 or not? Let's get an estimate, interval estimate. So what is an interval estimate? Let's just review. How would you do this? So if I gave you this on an exam and I said, you flipped a coin 1,000 times and you got 450 heads. Is that close enough or not? 400, let's say 40 heads out of 100. When is close enough? How many times do you have to flip this thing before you convince yourself that it either is fair or isn't fair? Okay? So what are you going to do? You're going to compute the probability of theta being in some interval. And how do we do that? I'm just reviewing last time.
We estimate using de Moivre-Laplace.
Exactly. We estimate using de Moivre-Laplace using the central limit theorem. So central limit theorem, in this case, de Moivre-Laplace, says that, well, I don't know if 100 is big enough, but let's pretend this is statistics and not pure mathematics. Let's pretend that 100 is big enough that if we take n times x bar, so this is just the sum of all of these Bernoullis, that's our binomial distribution with n summations. The expected value is n times theta, and the variance, remember the variance of we computed it last time, the variance of a single one of these is exactly theta. So the variance of each xi is theta times 1 minus theta. So the variance of a sum of them is that over n. So the variance of n times the sum of them is n squared times that over n. So in total we get n times that. So should I say this calculation one more time? Recall, so let's do it off to the side. So the variance of x bar will be the original variance divided by n. That's just a general calculation. And so of course the variance of n times x bar will be n squared times this. N squared times theta times 1 minus theta over n. And the n's cancel. All I'm left with is 1n, and that's the 1n here. So this is a binomial distribution. I've subtracted off its mean. I've divided by the square root of its variance. This should be close to Gaussian. That's the central limit theorem. Right? So the probability that this is less than something I want to be 1 minus alpha. That'll be my 95% confidence interval if alpha is 0.01. And here's where we're going to pretend. We'll pretend that it really is Gaussian. So if I put z alpha over 2, this approximation is that it's not really Gaussian, but the central limit theorem says, well, let's pretend it is Gaussian. And do you remember what these numbers are? When alpha is 0.05, in other words, 95% confidence interval, there's only one number that I have in my head, 1.96. Okay, so let's do 1.96 here. Okay. Now let's solve for theta. So if I divide both sides by n, so this probability, question? No. This probability is the probability that, let's just simplify a few steps at a time, x bar minus theta divided by theta times 1 minus theta over n is less than z alpha over 2. All I did is, there's an n on top and a root n on bottom, so if I divide top and bottom by n, I get rid of the n in the numerator because I'm trying to isolate theta, and then the root n here becomes a 1 over root n. Just algebra. Let me immediately multiply this to the other side, so let me put it here. Theta 1 minus theta over n, and then I can take it out of there. As I said, you'll have a homework problem where you actually solve for theta, but let's be even lazier and say that this is roughly equal to, not exactly equal to, this is roughly equal to the same thing, except now I'll say, so x minus theta being at most this means theta is bounded above and below by x bar plus something and minus something. And here's where we're going to be. So that's our first approximation, the central limit theorem. Our second approximation is to replace theta by an estimate for theta. What's our estimator for theta? X bar. Okay, so this is going to be z alpha over 2 square root of x bar times 1 minus x bar over n. And the same thing on the other side. Z alpha over 2 square root x bar 1 minus x bar over n. So this is the probability that the true theta lies in this interval. And if this interval contains a half, then there's this confidence, we have 95% confidence that the coin might be fair. But if it doesn't contain a half, we have 95% confidence that the coin isn't fair. Of course, it's not really 95% because we estimated theta by x bar and because we estimated the true binomial by the central limit theorem, by the Gaussian. Okay, but let's pretend. Let's call it an approximate 95% interval. So now all we have to do is plug and chug some numbers. So x bar is, let's work out what these things are. This is 1.96. X bar is 0.4. 1 minus x bar is, so 0.4 times 0.6, 0.24, and the square root of 0.24 is very close to 0.25 as long as we're approximating.
Because 49 squared is 2401.
I was going to do 0.2. Okay, so let's say this a little bit more slowly. Here we have 0.4 times 1 minus 0.4 times 0.6, right? X bar is 0.4, 1 minus x bar is 0.6. Okay, so that is 0.24, which is almost a quarter, and the square root of a quarter is a half. Okay, so the square root of this is close, let's just be rough, to a half. I'm dividing by n. Actually, I'm dividing by the square root of n. N was how many trials? We flipped the coin 100 times, so the square root of that is 10. Okay, so this whole thing, what we just estimated is that this whole thing is about 0.5 over 10. Question?
So like on exams, you just leave it like that?
Yes, on an exam you can just leave it like this. I want to do this actual calculation so that so that we see what this interval is. I want to find out, is that a fair flip or isn't it? Okay, so let's look here. So we have a tenth of 1.96 is 0.196, and I want that times a half. Is everybody with me? So what is that? That's actually not so bad. 18, half of 18 is 9, and then I have 16 left over, which is 8. So without doing anything, just a kind of rough, I made a little approximation here, but roughly this is going to be 0.098. And in fact, this is a slight overestimate, because 0.5 squares to 0.25, and we have 0.24. So this is, the truth is a little bit smaller than this. And now what's, yes, Jessendi.
How'd you get 0.196?
So all I did, the first thing I did is 1.96 divided by 10. The decimal place slid over, and then I want to multiply that by 0.5, which is the square root of 0.24, almost. Okay, so this is coming out to 0.096. What was x prime? X bar, rather. 0.4. 4 out of 10. So that with 95% confidence, theta lies in 0.4 plus this thing, which is 0.498, and 0.4 minus this thing, which is 0.4 minus this. So sorry, that's 0.302 or something. What's the significance of these numbers? I wanted to do a calculation so we get down to these numbers. Dylan.
You don't think it's a fair coin? You're 95% confidence on fair coin?
Why?
Because the value of 0.5 is not within.
Because a half is not in this range. Okay? So here's our possible values of theta from 0 to 1. Here's a half that I'm trying to see whether there's a chance that theta is actually true, a fair coin, whether if you flip a fair coin 100 times and you get 40 heads, whether that still makes sense with theta equals a half. And what we found is that with approximate 95% confidence, maybe so approximate that this isn't such a fair criticism because it's so close to 0.5, but modulo these approximations, if your true value comes out to 0.4, and you flipped it 100 times, it depends how many times you flipped it. If I flipped it 1,000 times and I still got 0.4, that's a much tighter, that's 0.0098. Actually, it's the square root of that. So if I flipped it not 1,000 but 10,000 times, that's correct. But anyway, the point is this interval, this 95% confidence interval, does not contain 1/2. So with 95% confidence, this interval, i.e., theta, is not equal to 1/2. So with 95% confidence, I can say this coin is not fair. And of course, that's not a true 95%, that's an approximate 95%. With approximately 95% confidence, the first approximation is the central limit theorem. The second approximation is that theta will be estimated by x bar. How about 99% confidence? Does anybody know what z 99% is? So z of 99% means alpha is equal to 0.01, right? That's 99%. So z sub 0.005, because that's half of alpha. That value, if you look up, is 2.57. So instead of going out to 1.96, you have to go out to 2.5, 2.57. And if I take half of 2.57, that is going to be bigger than 0.1. In other words, all of a sudden, this interval contains 0.4. So I cannot rule out with 99% confidence of the coin being fair.
You mean contains 0.5?
Contains 0.5, yes. So it's centered around 0.4. It has no choice but to be centered around 0.4. But once I want 99% confidence, this number goes up, the interval widens. So this was our 95% range. This is 95%. But once you go out to 99%, you cannot be 99% certain after 100 flips getting 40 heads that your coin is unfair. Let me write that explicitly in words. So, cannot be 99%, approximately 99% certain that the coin is biased. Okay? Does everyone understand the idea of this calculation? This is the beauty of the difference between point estimation and interval estimation. Interval estimation tells you, okay, I got an x bar of 0.4, but depending on how many flips I have, I can get an interval, and of course using approximations, the central limit theorem, and not doing the algebra to clear theta out of the x bar, which we could do, and that's a homework problem. That'll give you a more precise, that'll give you one less approximation. And actually here's a good exercise, an optional exercise if you want to really understand this. Compare the true interval that you get without substituting x bar for theta there from your homework and see if it's still missing a half. Does everyone understand? Let me write that down. Here's a good optional exercise. When you do your homework, so don't approximate theta times 1 minus theta by x bar times 1 minus x bar in this, you know where I'm talking, this error term here. And if you do that, what is the interval, the true numerical integral at 95%? Does it contain a half? Does the true numerical interval and again, it's still not the true 95% interval because
We're estimating with CLP.
perfect. As Taylor said, because we already used the central limit theorem instead of the true binomial distribution. Why can we just numerically compute the true binomial distribution?
You can involve a lot, I guess.
Well, we need to know what theta is in order to compute the true binomial distribution,
Yeah, that's right.
which is begging the question. That's circular. We're trying to get an estimate for theta. So this isn't an instance of don't be lazy, don't compute a t by a z. There is no computation because the outcome of the computation depends on theta. Let me write that down. Note we're not being that lazy, in computing and in estimating that this thing, theta times 1 minus theta times n, is approximately the normal because the true distribution of this is a normalized binomial and it depends on theta. So without knowing what theta is, we can't get estimates for z, theta, the binomial.
So at this point, the n would be in the numerator of the denominator term, right?
So,
Because the variance on the bottom is not equal, right?
It would be n times theta.
this is n times. I'm not dividing by n. That's a
Oh,
parenthesis.
Okay. I thought it was right. Okay.
Let me write it the way you want to see it. I just put it at the end. So this is theta times 1 minus theta divided by n. This is theta times 1 minus theta times n.
Okay.
Maybe that n looks a little small. Is that better?
Okay.
It's not in the denominator. So we can't compute this without knowing theta. This depends on theta. Unlike a t-distribution where we know the degrees of freedom. That's just a function of how many samples we got. It doesn't depend on the parameter that we're trying to estimate. Does that make sense? Should I say that again? Did everyone follow the philosophy here?
Yeah, it's out of necessity, not because we're being lazy.
Yes, here it's out of necessity, not laziness. So it's out of necessity. Out of necessity. Unlike the t-distribution being approximated by a z, where we are being lazy. Dylan.
Is there like a binomial correction formula for when you use approximate normal distributions?
Yes, and that binomial correction formula, so we know the rate at which a true binomial approaches this. I mean, that difference is an explicit function, but it's also an explicit function of theta. That's the problem. So the quality of the approximation depends on if theta is actually, if the true theta is 0.1, it's going to take a lot longer to get to a Gaussian than if the true theta is 0.5. So again, without knowing what theta is, we're kind of stuck doing this. Okay? What if you saw 30 coin flips, 30 heads out of 100 coin flips, or 5 heads out of 100 coin flips? How certain would you be that the coin is unfair? Right? You can do all kinds of gymnastics of questions of this form, which just are nothing more than algebra on that basic. The basic inequality is right here. This is the basic inequality with these approximations. And you don't have to do these approximations. That's the homework. But this is the basic inequality that gives you a range for theta. Then you can do whatever question you want to ask. You can, if I see 0.1 as my x bar, how many values of n do I need to compute here to know with 99% certainty that it really is biased? Okay? This is just which variable are you solving the algebra for? Does that make sense? All right. Any questions? So that's just review. That was a review of this is called proportion, estimating proportions. What proportion of the coins do we expect to be fair? What proportion of the population is going to vote for candidate A versus candidate B? You do a direct estimate of binomial by the central limit theorem. Now the next thing is, what about comparing two proportions? Let me put this here. So next, comparing proportions. So let me give you an explicit example. Here's our example. So this is a difference of Bernoulli's, basically, i.e. difference of Bernoulli or binomials. Binomials. Bernoulli. Depending on how you think about it. So let's say you have 132 out of 200 male voters prefer candidate A to B, prefer A to B, but 90 out of 150 female voters prefer candidate A to B. So what's the ratio? 132 out of 200. Did I write these down, or am I going to have to compute these things in front of you? So let's call the males. I guess let's call these candidates 1 to 2, so that I can call males A and females B, or brand of light bulb A and brand of light bulb B. Okay. So what is my X bar A? So again, we're treating whether or not whether or not a voter likes candidate 1 versus candidate 2 as a coin flip. And let's say candidates, these voters are independent, okay, and identically distributed. You always have to swallow some massive pill to be able to do any of these estimates, right? We're going to make this assumption. Is it a fair assumption? There's an entire theory of why that's not a fair assumption, how you fix it, and how you sort of correct these things, but let's ignore that. These are Bernoullis. Every male voter is a Bernoulli, every female voter is a Bernoulli, but their parameters might be different. So there's a parameter. This is our estimator for the Bernoulli parameter for males. We have another estimator for the Bernoulli parameter for with females. So what's our guess for males? Altogether, what's the proportion? We're comparing proportions. Yeah, 132 out of 200. 132 out of 200. So this is, what is it? Well, it's just half of 132. That's 0.6, and then 12 is 6. Yep, 0.66. Okay. How about women? What's the proportion for women? 90 out of 150.
Plus 3/5.
Yep, 3/5, 0.6. Okay? 3/5 is 0.6. So men prefer candidate A to women. Both prefer candidate A to candidate B, by the way. Maybe that's all we should care about, but it's a newspaper, so we have to write a story. So therefore, men prefer candidate A. Men prefer candidate 1 to 2 more than women prefer candidate 1 to 2. That's what the research is saying. How confident are we in that statement from these numerics? So let's find a confidence interval. What we want is a confidence interval for theta A minus theta B. Okay? Is that clear? So what are we going to do?
Standardize it.
Yes, exactly. We're going to do exactly the same thing we've been doing all along. We're going to do this. We're going to pretend that this is a Gaussian in each of the independent experiments, poles. So x bar A minus theta A divided by square root of theta A 1 minus theta A divided by NA, the number of trials, in other words 200 in the case of men. That's a standard Gaussian normal. This is a standard Gaussian normal. Actually, this is a not standard Gaussian normal. This is a normal with mean 0, but variance exactly what was in the square root. Theta A times 1 minus theta A divided by n. This is Gaussian, approximately. That's the central limit theorem. So this should be, not just is it distributed like this is an exact symbol, but let's do that. So this is the central limit theorem. Similarly, x bar b minus theta b is central limit theorem distributed like, we've subtracted off the mean, so it's mean 0, but the variance is still the variance, theta b, 1 minus theta b over n, b. And the difference of two Gaussians, so the negative of this is still the Gaussian, and now I have the sum of two Gaussians, which is to say the difference of two Gaussians. So, bless you. Here we have xa bar minus theta a. That's a Gaussian. Xb bar minus theta b. That's a Gaussian. The negative of this Gaussian is still Gaussian with mean 0. So this is a sum of two Gaussians with mean 0. This is distributed, again, I'm approximating these distributions, as a Gaussian of mean 0 and what variance?
Sum of the variances.
They're independent, so it's the sum of the variances. Okay? So the sum of the variances is theta a, 1 minus theta a over na plus theta b, 1 minus theta b over nb. Okay? And what's the beauty of this? We're going to do one stitch of algebra. Is that this is an interval for the difference that we're interested in, namely theta a minus theta b. So we can capture theta a minus theta b as x bar a minus x bar b, but we know more. We know that that will be a Gaussian with mean 0 and this variance. So that's it. So the probability that x bar a minus x bar b differs from the true theta a minus theta b divided by the square root of theta a times 1 minus theta a divided by the number of trials plus theta b times 1 minus theta b divided by its number of trials. The probability that in absolute value this differs from z alpha over 2, well, is equal to, not really, because we're using the central limit theorem, alpha, 1 minus alpha. Now we again have the problem that the thetas, I can't just move this to the other side. Well, I can, but then I don't have an interval for the thetas. You asked the question? Oh. So what are we going to do? Approximate the thetas here by the x bars. But now it really is out of necessity, because if you try to do this algebra, it gets really hairy. In fact, you can't really get rid of them in any nice way that's reasonable. So we'll approximate this by the probability that this difference, xa bar minus xb bar minus theta a minus theta b, the true theta a minus theta b, is bounded by z alpha over 2 times the square root, and here I'm going to replace thetas by x bars. This has only things that we can estimate from the data. So if we want an approximate 95% confidence interval for whether men prefer candidate 1 to candidate 2 more than women prefer candidate 1 to candidate 2, here's an estimate for that difference in terms of the true 0.6 versus 0.66. And we want to know, does this interval contain 0? is there a significant difference between how much they like candidate 1 over candidate 2? By sticking in 1.96, if we're doing 95% confidence interval. And then these are all things from the data. X bar is 0.66, X bar A, X bar B is just 0.6, NA is, they asked 200 men, but they only asked 150 women. Any questions on comparing proportions, differences between proportions? Should you memorize these formulas? I don't think so. I think you should just understand them. Is this stuff easy? This is supposed to be easy. This is supposed to be like, how can I get something to look like something I know already, the distribution of which I can just, numerically compute what my confidence interval is. I hope you're getting the feeling that this is easy. Yes, no, maybe?
Well, it's ugly. It's easy, but ugly.
It's the algebra. I mean, it's not that ugly. It's kind of a little, okay, depends on of course your definition of pretty, but yeah, I agree. It's not the cleanest thing, but it's actually, is it any uglier than a chi-square distribution?
No, that collapsed at the end, so it was satisfying.
It was satisfying? Good, we're about to do something very similar. So, but yeah, this doesn't collapse at the end, but it's a symmetrical formula in A and B. It's a nice kind of, yeah, Noah?
Yeah, just a question about how you got from the previous step to the last step.
From here to here.
Yeah.
Is by replacing the thetas that we don't know. So this is the last step. This is to replace thetas by x bars. And the same thing with b. So what I really want is this on the other side, but then it doesn't give me an interval for theta. Or certainly not for the difference of theta. So that's really what happens. If you start doing out this algebra, you will not recover something that's a difference in the thetas. Unlike when we only had one of these, and you can do out the algebra and get just theta, isolate theta on one side. This is just simply not a function of the difference. Because if you just look at the shape, I mean, it would be a miracle if it was. And we get a lot of miracles in mathematics. This isn't one of them. Okay? Any questions? Moving on. Okay. Sometimes what you want to estimate, our next topic, this whole chapter is on estimation. Sometimes what we want to estimate is variances. How would you estimate a variance? So let's talk about estimating variances. So we have some, again, Gaussian. Everything that we're talking about is Gaussian because, well, not everything. We had some Bernouillis, but these are kind of the most basic units by the central limit theorem. Okay, so let's go back to IID Gaussian. And what is our estimator? So how about a point estimator for sigma squared?
S squared.
Is exactly sigma squared estimator is s squared with the correction, with the Bessel correction, right? Let me remind you, s squared is the sum as I goes from 1 to n of each observation minus the sample mean divided not by n but by n minus 1. And what we showed is that n minus 1 times s squared, in other words, don't do this, don't divide by n minus 1. This divided by the true variance is a, what's the distribution of this? Chi-squared. This is a chi-squared. This is distributed like a chi-squared with n minus 1 degrees of freedom. Okay? And let's recall just one more time what the PDF, probability density function of a chi-squared is. So
this is supposed to be a square or something somewhere, right? The deviation.
Ah, yes, thank you. Thank you. I'm trying to compute a variance. So I'm trying to compute the expected value of this minus this squared. So I do it not on the probability, which I don't know, but I do it on the observed sample. So this is the observation minus the observed mean. I compute the square of that nice sum. Thank you. Everybody saw that, right? Zach was just the only one to pipe up, but everybody knew that the formula was missing a square there? Okay. What's the PDF of a chi-squared? There's some constant. Yeah, let's do the n minus 1 degree of freedom. So it's 2 to the n minus 1 over 2 gamma of n minus 1 over 2. That's less important, and you can work it out. But what is the density itself? How does a chi-squared? Oh yeah, chi-squared looks like a gamma. So it's going to look like an e to the minus t, except it's not a gamma. It's off by this factor of 2. If t is my dummy variable, that factor of 2 is responsible for this power of 2. And then t to the power, degrees of freedom over minus 1, degrees of freedom over 2, and then my favorite 1 over t at the end. So this is our n minus 1 degree of freedom chi-squared. Now what does that look like? You remember what it looks like as a function? So by the way, this is only if t is positive. Chi-squared is the square of a Gaussian. These are squares of Gaussians. So t is positive, so here's t. There's nothing until you get to 0. Here's f chi-squared. Now it depends. So the behavior at infinity is always the same. This is some polynomial times an exponential decay. So it's always decaying exponentially. So that's e to the minus t over 2. Now what happens as you come up here? If n is equal to 1, if n minus 1, if the degrees of freedom, n minus 1 is equal to 1, then I get here so this is a 1/2, but divided by t. So the total power is t to the minus 1/2. Okay, let's write that down. So let's look at this. If n minus 1 is equal to 1, if we have 1 degree of freedom, then this looks like t to the minus 1/2 in total. Or if n minus 1 is equal to 2, then this is 2 over 2 times 1 over t. So 2 over 2 is 1, and I have t to the 1 divided by t. Kiana? It's 1, so it's t to the 0, which is 1. So there is no power of t. I'm trying to understand what's happening at 0. To see what's happening at 0, well, this is going to 1, and this is some polynomial in t. This thing looks like, what does t to the minus 1/2 look like at 0? Not t to the 1/2, t to the minus 1/2, 1 over square root. So it's going to blow up, right? It's 1 over a very small number. So if n is equal to 1, it looks like that. This is n minus 1 is equal to 1. N minus 1 being the degrees of freedom. Because it goes like square root 1 over square root x. Okay? How about when n minus 1 is equal to 2, it's going to a constant. Yeah, not exactly 1, but almost. Yeah, it's going to some constant. So it comes like that. This is if n minus 1 is equal to 2, goes to a constant. Otherwise, this power is some positive power, right? Everybody see that? Otherwise, this is a positive power, and a positive power, so t to the next one is going to be what? T to the 3/2 or something? T to the 1/2, when I include the 1 over t. So t to the 1/2, now it's the picture that Taylor was saying. T to the 1/2 is going to come back down to 0. So all the other ones come back down to 0 with various degrees of excitement. A large power of t goes to 0 very quickly. Okay, so all the others, if n minus 1 is bigger than 3, all the other ones come down like this. But look at the shape of this. Can we now, so what are we going to do? We're going to say we know exactly what these curves are. These functions do not depend on sigma. So we can use this chi-square distribution as an estimator for sigma. for sigma squared. Does everybody follow? Does everybody anticipate what my next step is going to be? So here's this expression. That means that the probability that n minus 1 s squared over sigma squared lies between two numbers is given by an integral that doesn't depend on sigma. So we can evaluate it. If we want this to be alpha, let's say 1 minus alpha, well, if we want some interval that does this, maybe we want to take alpha over 2 of the mass from here and alpha over 2 of the mass from here. But we no longer have a symmetric density function. So we have to do it in 2 steps. So let's define. So let's say that chi squared alpha comma n, well, let's say n minus 1. So n minus 1 is the degrees of freedom. Since I'm using n minus 1 as the degree of freedom everywhere, so we don't have to change variables later. This is the number. This number, wherever it is, that's the number, so that this integral, and of course it depends on what n is, that integral has size alpha. Okay? So if I want to capture half of the tail over here, what should I put here? I just put the usual thing, right? Chi squared alpha over 2 n minus 1. Whatever this number is, which you can compute numerically, by which I mean Google and Wolfram alpha. It doesn't depend on sigma. It's just this formula, which has no sigmas in it. Okay? How do I get the back tail? I also want to throw away the back tail. So I should put some value here. What's the value that will throw away the initial alpha over 2? Well, if the initial part is alpha over 2, how big is the tail? 1 minus alpha over 2. 1 minus alpha over 2. And look at the definition of this number. It's the place where the tail has size 1 minus alpha over 2. But the inequality is going this way, so that's going to capture this side of the tail. So this constant is capturing that side of the tail, that constant is capturing that side of the tail. That gives me a two-sided interval where I've removed alpha over 2 on both sides of the probability on both sides. Does that make sense? There's a homework problem that you can do this in terms of, anyway, there's no need for any further gymnastics. There are all kinds of things people used to do so you didn't have to compute things on both sides. There's no need for any gymnastics, just compute this numerically to as large precision as you want. Jess and Dee.
So those are both sides of the tail, right?
Yep. So each of these tails is removing alpha over 2. And so what I'm left with is 1 minus alpha. That's the bulk. I want to know, when is this thing in the bulk? Of course, I could have chosen, maybe I care a lot more about this tail, or maybe I care a lot more about that tail. I could have chosen alpha over 4 and 1 minus 3/4 alpha. That's also a 1 minus alpha. So your confidence intervals don't have to be symmetric. Another confidence interval, 1 minus alpha times 100% confidence interval is the probability that this thing, n minus 1, well, we're not done getting we want to isolate a sigma squared. So we're going to do a little bit of algebra that tells you what sigma squared is. But let's just see. Another confidence interval is if I'm much more concerned about the top than the bottom, then maybe I'll say I want alpha over 4 of the mass to be here, and 3 alpha over 4 of the mass here. Alpha over 4. This will cut off alpha over 4 of the mass. 3 alpha over 4 will cut off 3/4 alpha of the mass from the initial piece. There's no reason to choose half alpha and half alpha. All you want is some confidence interval that's giving you a bulk of 1 minus alpha. And we didn't really think that was necessary when we had a symmetric distribution, but now that it's not symmetric about x, maybe we do care. Does that make sense? Taylor?
Sorry, can you explain why we chose 1 minus alpha half over 2 as the bottom?
Yes.
thing?
So let's go back here. What we want to know is, where is this number? What is this number? What's my 1.96 when it was z alpha over 2? Where is it? I want to know a number that cuts off the tail, not the tail alpha over 2, but the initial alpha over 2.
Yeah.
But if this weight, if this mass is alpha over 2, then the rest of it has mass 1 minus alpha over 2.
Yeah, I get that part.
I could have made two definitions. I could have defined this chi-squared tail alpha and initial alpha. But actually, once I've defined the tail alpha, this number determines two numbers.
I mean, like, I kind of understand that, but when I try to think about it as if we chose alpha as like 0.05, so
Yes.
then we had chi-square of 0.025, and then we had
Yes.
chi-square of so then if we have 1 minus 0.025, I get kind of confused because then don't we have like 9 point
Perfect.
some.
Perfect, perfect, perfect. Let's do exactly that. So here I still have my chi-squared variable. This is chi-squared of 0.025, n minus 1. And this is chi-squared of 0.975. 0.975 n minus 1. So let's look at what that's actually saying. Let's pretend this is my chi-squared, f chi-squared. It's clear what this one's doing. I want wherever this number is, let's just call it chi-squared 0.025 with this number degrees of freedom. I want this mass to be 0.025. Right? Now, what is this saying? This is some number. Let's call this number chi-squared 0.975 with n minus 1 degrees of freedom. I want some number so that this whole mass has mass 0.975. But if this massive tail, this is a gigantic tail, and is almost all the mass, how much is left here?
Okay, yeah, that makes sense now.
Does that make sense? Thank you for asking that, because I'm sure there are lots of other people that were confused. That means all that's left over is this. Does that clarify? Justin.
If that's the case, why are we subtracting 3/4 for the next one instead of 1/4? Or alpha over 4 or 3 alpha?
Okay, let's do the next one. Let's do the next one with exactly the same computation. So this picture was for the original, and now we need a new picture. Here's my chi-squared, and let's see what this is doing. Okay, so what was I saying there? I was saying, give me alpha over 4 of the mass off of the tail. If I take 1 minus alpha over 4 of the mass here, all that I'll be left with is alpha over 4 of the mass. And in total, I'll have alpha over 2 of the mass. I get a too high a confidence interval. Instead of a 95% confidence interval, I get a 97.5% confidence interval. So if I want the mass that I'm taking off of the tails to add up to alpha, if there's 3/4 alpha here, if there's 1/4 alpha here, then I can take a full 3/4 alpha. Or again, if all I care about is the top, maybe don't take anything off. Put all of your alpha up here. Right? Or, I'm just telling you all the different ways you can write alpha. here's alpha itself. Here's chi squared alpha with nothing at the bottom. That'll give you a one-sided inequality. Actually, you'll see in a second it'll give the wrong inequality because sigma's in the denominator. That'll give you a lower bound for what sigma is. Does that make sense? Are these things getting clarified by all the questions?
So you do the 1 minus because you want the opposite of the cumulative distribution?
Exactly.
Okay.
Well, it's already the cumulative distribution. This is just historically how people decided to name these numbers. What's the standard? What's the nomenclature? And the nomenclature is this number means how much of the tail of a chi squared with n minus 1 degrees of freedom gives you this amount of area.
Yeah.
So it's all about tails.
Yeah.
And we could have said how much of the cumulative gives you that.
Yeah.
But
That's fine. Right?
that's not what human beings decided to do. Human beings decided to tabulate these numbers, and so what you look up in the table is this. Although you could, this literally is the cumulative that gives you 0.025, the inverse cumulative function.
Inverse, yeah. So it's 1 minus because it's the inverse cumulative.
No, what I mean by the inverse cumulative is I want to know the cumulative function is given a
Literally
value
inverse, like what point?
as a
Not
function.
area.
Yes, what point?
Has the
This
area.
is saying what point on the cumulative distribution function has this area.
Yeah. So that one actually is the inverse cumulative.
Literally, yes.
The inverse cumulative.
And this is the inverse of 1 minus the
The
cumulative.
1 minus cumulative. Okay.
So if you didn't follow that, that's okay. Just there's human beings decided how they want to call these things. They decided to call them the tails. Once they had tables, they didn't want a new thing for the cumulative. They just said, use a massive tail, and that captures where the front of it is. There's nothing deep here. But is this clear? Even though it's not deep, it could certainly be confusing. Who's confused? Are you guys lying, or are you really okay? Ernest, raise your hand. Who's confused? Okay, all right. Thank you, Ernest. All right, so we're not done because we still have to solve for sigma here. Let's go to the half-half. So let's go back to this half of the tail, alpha over 2 taken away from the end, alpha over 2 taken away from the front. Just to see what's going on. Now all we have to do is solve for sigma. This is completely elementary. You flip this thing and so let's do it. So a 1 minus alpha percent confidence interval for sigma squared, again coming from Gaussian IID samples, is given by the fact that the probability. So let me multiply by sigma squared and divide by this number. So the sigma squared will wind up in front. So I get a 1 minus ns squared divided by chi squared alpha over 2 n minus 1. So the equations switch sides. All I did is I multiplied sigma squared here and divided this to the bottom. So the upper bound became a lower bound. And similarly, I moved sigma squared to there and put this down here. That gives me an upper bound for sigma squared, n minus 1 s squared divided by chi squared of 1 minus alpha over 2 n minus 1. So this interval, let's finish the computation. This is equal to 1 minus alpha. But it would also be equal to 1 minus alpha for any convex combination that adds up to 1. So if you care much more about an upper bound for sigma squared, or maybe you care about a lower bound, you want there to be fluctuations, then you can adjust the balance here. Is that clear? All right, we have one more thing to cover. So that was estimating variances. Why were we estimating variances? Well, we want to know, if you recall, if we had two estimators, let's say theta hat 1 and theta hat 2 for the same parameter theta, we called one more efficient than the other if the ratio of the variance, we looked at the ratio of the variances.
So, I mean, the efficiency, like, they're different conventions. So are we using the ratio in the opposite order for the efficiency, so that a higher efficiency is better? Like,
Let me write down the equation and then you'll see.
Okay.
But yeah, so it's more efficient if the ratio of the variances of 1 to 2 is less than 1.
Yeah. So a higher efficiency, that's what I think in some books, or maybe in this book, they did theta 2 to theta 1.
We can, yeah, if you want to attach names to these things, you can. But if you just understand what ratio you're taking, then you can always. Sure, I'm happy to define. I mean, so different places define them differently.
Yeah.
So as long as you understand what you're computing,
Yeah.
then it's clear.
Expression.
Okay. So the efficiency of one to the other to the other. And I won't specify which one is 1 and 2, so that I'm safe, regardless of which book you're reading, is the ratio of the variances. So the variance of theta 1 to the variance of theta 2. And of course, if one has a smaller variance, then this ratio will be less than 1. And the smaller variance is the one that gives you the tighter estimate on the true parameter. Okay, so how would you estimate not just the actual variance, but a ratio of variances? So how about, how can we get an estimate? This would be a point estimate. This is a point estimate for this ratio. But how can we get an estimate for an interval estimate for the ratio of two variances? This is a new distribution that we skipped when we were having our discussion. How many people know what it's called? 1, 2, 3. Okay. This is called an F distribution. This is called, we need a new distribution, need an F distribution. And I always have to double check the constants. So by the way, this is, F is Fisher's F, a very famous statistician from 100 or so years ago. So the F, let's just define it. Let's work out the constant. Here's what an F distribution is. This is going to be estimated by S1 squared. This is estimated by S2 squared. Each of these is a chi-squared random variable with some number of degrees of freedom. So definition, an F distribution is, let's call it U, which has n degrees of freedom, and V, which has m degrees of freedom, where U is chi-squared with n degrees of freedom, and V has the distribution of chi-squared with m degrees. It's clear why you would want to do this, I hope. What's a chi-squared with n degrees of freedom? Well, it's n minus 1 s squared over sigma squared, where that's the first value. Okay, we'll get to the application. First, let's derive what the F distribution actually is. So we need to know what this density function is. That's just the definition. Let's compute it.
And U and V are independent.
And independent, thank you. And U and V are independent. Very important. Let's put that here. Okay, so an F distribution is a ratio of two chi-squareds divided out by their number of degrees of freedom. Let's compute the PDF. This is going to be a calculation. Are you ready for it? Or is it too late in the day to do a calculation? It's going to be very similar to the other calculations we've done. In fact, should I let you work on this for like 5 minutes? No, you're too tired to. You're not in the mood. Let's do it together. We can. This is easy. This is easy. Okay. Ha! I didn't grab a blank sheet of scratch paper. Okay. So let's derive its PDF. First of all, what's the support of the PDF going to be? Can we see that easily? Taylor's right. 0 to infinity. U is a chi-squared. V is a chi-squared. Both of them are positive. The ratio of positive reals is a positive real. Okay? So the PDF of an f is 0 for t less than or equal to 0. Now we have to derive the rest. So what's the probability that an f distribution is at most a? We're going to take this, we'll differentiate with respect to a, or alternatively express it as an integral from 0 to a of something, and that something will be the PDF. Okay. We have two variables, u and v. Do you have a guess as to which one we should integrate first? Other than Yasa? I would have guessed u, and you will see very quickly why it's better to do v on the outside.
Well, because you can multiply.
Yeah, because v is in the denominator, so it's easier to mess with u, because u is going to have nice things. So let's integrate in v. So little v goes from 0 to infinity, dv, and then the PDF of a chi-squared with m degrees of freedom of v. So far this is saying just integrate over all of v with its PDF. And then I want to integrate my u with its PDF, which is f chi-squared n degrees of freedom of u du, except it's not going from 0 to infinity, it's restricted to this condition. So f is u divided by n over v divided by m. So it's restricted by the fact that u divided by n over v divided by m is at most a. Because that's the condition I want to capture. F is at most a, that means u divided by n divided by v divided by m is at most a. Does this ring a bell? I think it's very good to break these calculations up, because now we've done things just like this, but it was a couple weeks ago, so hopefully your neurons are already firing and you're kind of seeing where this is going to go. And you could probably do it by yourself, but you've already voiced the opinion that you want to do it together. So if we're keeping v fixed on the outside, a is, again, the amount that we're integrating up to, n and m are fixed constants, so u is the only variable here. So what does this mean for u? This is true if and only if u is at most a times v over m times n, which I can write as that. In other words, we're not integrating up to infinity, we're integrating up to here. Does everybody see that? It's exactly the same thing as what we did when we were computing a t-distribution, except with different. That was a ratio not of two chi-squareds, but of a Gaussian to a chi-squared with a square root. It was much more technical. This is a much easier computation. At this point, should I cut you loose? Justin, you ready to do it? Kiana. So what we're saying is there's only one condition, which is that this ratio be at most a, and we want to find the probability, the weight of all the parameters u and v for which this inequality holds. So let's let v be completely free. Let's range over all possible values of v. I mean, the first thing we did is we said, let's range over all possible values of v and all possible values of u for which this condition holds. Then we simplified this condition and saw that if we let v range freely, then u is restricted to this interval.
So you could also have done unrestricted u and do the same thing.
Yep, we could have also done unrestricted u and then solved for v, and it would have been okay. It would have been a lower bound for v, and the computation would have been a little bit more confusing, I think. There's nothing algebraically more difficult about it. You could do it either way. I mean, in fact, maybe the simplest thing to do at this point is to literally take the derivative with respect to a and just follow the fundamental theorem of calculus. But I have a feeling that's something that's going to confuse people more than doing a few manipulations on a double integral with changes of variables that we've done 6t times. So you're absolutely right, Kiana. We could have done this in either order. I'm just, with hindsight, choosing one that's going to make the algebra come out nicer. Other questions? Can we go? Can we do this like relatively quickly? Because I want also, okay. I also want to be able to use it at some point. All right. So what is this? What is this? We're going to make a change of variables. Let's make a new variable. What should I call this variable? T? Q? You're just messing with me? Give me a not Q, come on. T. Pi? T. Okay, so T will be equal to U times something, or maybe divided by something, with the property that instead of going up to A times V over NM, it's just going to go up to A.
Yes, we divide by the
So let's divide by the crap that we don't want. U divided by V, U divided by V, time in the denominator is an N over M, so let me multiply that by M over N. Which, by the way, as usual, is exactly the original variable. So we're making a change of variables from U to F, except it's still a function of V, which is why the V integral is on the outside. If for any fixed value of V, we make this change of variables. Okay? Now we need to know what these distributions are to make the changes of variables. So this is equal to, let's leave the V integral alone for a second. F chi squared with m degrees of freedom of V dV. I need to know what my chi squared of, what this chi squared is. We just said what it was. Where can I put it? Let me put it here. Recall that F chi squared with n degrees of freedom of U is equal to 1 over 2 to the n over 2 gamma of n over 2 times e to the minus u over 2, u to the n over 2, 1 over u. That's just what a chi squared is. So when I make that change of variables, and by the way, what is dt? Actually, what is dt over t as compared to u? du over u. We don't even have to do it anymore, right? This is second nature. That's the beauty of having a 1 over u du. So that part we don't have to worry about. The integral will go from, these constants are all positive. The constants that we're multiplying are all positive. So if u ranges from 0 to infinity, then t ranges from 0 to infinity. But we're not ranging up to infinity. U will go up to a v n over m. So if I put a v n over m for u, I get a v n over m divided by v times m over n instead of n over m. So it goes up to a. That was the whole point of that change of variables. Again, du over u turns into dt over t. I have some constants, 1 over 2 to the n over 2, gamma of n over 2. I have a factor of e to the minus. Instead of u over 2, that's u is equal to t v n over m. T v n over m over 2. That's from what u is in terms of t. Let me write that more explicitly maybe here. U is equal to, I'm just solving this equation for u, t times v times the reciprocal n over m. Kiana, this is okay so far?
What does that dt equals d over
dt over t, that's a dt over t. dt over t is du over u. They both have the same multiplicative factor. So I've taken care of the constant, I've taken care of the exponent, that's the constant, that's the exponent. I need a u to the n over 2. The 1 over u we've taken care of, that's dt over t. 1 over u du. How about u to the n over 2? U is this, so I get a t to the n over 2, t to the n over 2, times a factor, what's left over is v n over m to the n over 2. Does everybody see where that came from? I had a u to the n over 2. That became all of this. Because of what u is in terms of t. U is t times this, so u to the n over t is t times this to the n over 2. Almost there? Okay. Now all we have to do is do the v integral. Exactly like we derived a t distribution. An f distribution is derived in exactly the same way, it's just the functions involved are slightly different. Actually, it's very, very close. Okay, so let's do the v integral. So I'll change orders and I'll do the t integral on the outside. So the t integral on the outside is an integral from 0 to a dt over t. So I've taken care of this, I've taken care of this. Let me pull the t out, t to the n over 2. Is there anything else I can pull out? I guess I can pull out this constant, 2 to the n over 2, gamma of n over 2. And all that's left is the v integral. You see, this has v's in it, and this has v's in it, so I can't pull it out just yet. So let's do the v integral. V goes from 0 to infinity. I have a factor e to the minus t v n over m over 2. I mean, I'm writing it in kind of a silly way. There's a factor of v, let's write this as v to the n over 2, and n over m is a constant, so let's pull that all the way out. N over m to the n over 2. So now I've taken care of everything except the actual PDF, the original PDF of v. Everybody see that? So the original PDF of v was 1 over 2 to the m over 2, because it has m degrees of freedom, gamma of m over 2, and then e to the minus v over 2, v to the m over 2, dv over v. Not so bad. I am basically out of time. So what are you going to do? You combine the e's. So here's what you're going to do at home, and then we'll see how to use this next time. You're going to combine the e's. This is an e to the minus v times, there's a 1/2 here, and there's a, I guess I could do the 1/2 in common, there's a t times m over n, and then a 1/2. Let's put the 1/2 together. So you make a change of variables. This thing is equal to some other variable w. And then you get a bunch of stuff. And at the end, what you get is that the PDF, let me just tell you the answer. The answer at the end of the computation is gamma of n plus m over 2 divided by gamma of n over 2, gamma of m over 2. Those are constants that came from here and here. The powers of 2 will cancel. This gamma will be what results in this computation. And the distribution is an n over m to the n over 2. That's that constant that we already had. And finally, this last thing, 1 plus, what variable am I using? T. 1 plus t times n over m. That's what's in here, raised to the negative n plus m over 2 power with a t to the n over 2 dt over t. All right, that's the computation. So the inside is your PDF. This is f sub f of t. We can do it more slowly next time, but I think the algebra is just algebra. You, I think, understand everything about how to do these calculations. We'll see how to use it on Friday. All right, see you then.